Okay, hi everyone. Welcome to another episode of Science and Technology Q&A for kids and others. So we seem to have all kinds of questions here that are left over from previous times. So there's one from Deceive here that asks, is it possible for there to be a different world or civilization deep in the oceans that we do not know about? Well, depends what you mean by a world or civilization. If let's take that in several different directions. So one possibility is, could there be, deep sea fish that have somehow managed to achieve some high level of civilization and have built fish cities and are doing elaborate things under the oceans? I don't think we could rule that out. I think we have at this point. So what's known about deep oceans? There is what's usually called bathymetry data, depth of the ocean data for the whole Earth. And that's been found by, I think, mostly the way. So how do you find out how deep the oceans are? People always used to just have a weight at the end of a string, basically, and just let that out from a ship at a particular place and just see how far you had to let it out before it hit the bottom of the ocean. That in more recent times, being able to use sonar, that is having pulses of sound that you put in the water and you listen for the echo of the sound coming back from the bottom of the ocean, that's the more recent way to do to find out depths of the ocean. I mean, one of the surprising things about the oceans is that sound travels very well underwater, particularly in the deep ocean where the water is very still. And one of the sort of surprising things is that sound can travel all the way across a big ocean when it goes into the deep ocean. What tends to happen is that the way the pressure changes in the ocean, it's like the refractive index, the speed that sound goes at is such that the sound will get kind of pulled into the deep ocean, and then it goes through this kind of channel in the deep ocean where it can go without really being attenuated at all, without getting less loud at all, and it can go thousands of miles and then be detectable. And that's a trick that the whales use, and that's why whale songs can presumably be heard by whales all the way across the ocean. It's kind of we think of ourselves very proudly as being a civilization that has managed to have instantaneous communication around the world using fiber optics and radio communications and so on. But actually, the whales sort of already have it with sound in the ocean, which can propagate a long way. Now, in terms of what might exist in the oceans that we don't know about, it's been not that long. For example, hydrothermal vents, places where there is kind of hot stuff that comes from that's associated with the hot interior of the Earth, kind of bubbling up through the ocean floor. People had thought, for example, there's nothing alive in hydrothermal vents, but because they're full of sulfur and other kinds of chemicals that don't seem to agree with most kinds of life. But then, I'm not sure how long ago, a few decades ago, life was discovered in hydrothermal vents. And in fact, interesting and unusual kinds of life that worked in ways that were different from the ones that we were used to were discovered there. So you might say, well, there's nothing there, but that might not be true. Now, if we ask the question, sort of what level of civilization, so to speak, might be achieved by the deep ocean things that are crawling around on the ocean floor, or the fish, or the mammals, aquatic mammals, or whatever, this question of sort of what level of civilization is achieved, that's always a somewhat difficult thing to define, because we're used to our particular civilization, our way of communicating using language, our way of building structures and so on. Is that the only way for a civilization to be and still be a sort of a sophisticated civilization? I don't think we can really answer that. It could be the case that if we define things to be sort of human-like, it could be the case that the dolphins have been telling epic stories to each other, just like the ancient Greeks did with or many other kinds of civilizations have done, have been telling stories to each other and kind of each one is remembering them, and then they're passing them on by making sort of dolphin sounds and so on to other dolphins. And there's a whole story of what's happened there. Do we see dolphin houses having been built? Well, no, we don't. But I'm not sure that we would necessarily say that the lack of sort of shelters and things that are permanent objects that have been built is necessarily characteristic of civilization. I think the presence of artifacts, things that were created in a certain way to be used, again, I'm not sure how characteristic of civilization that is. I mean, people have tried to sort of get a rating of civilizations, like they say, well, how tall are the structures that have been built by a particular time in history, or how many levels of administrative kind of structure, how many levels of from the boss to the sub-boss to the sub-sub-boss and so on, how many levels exist in kind of government organization, things like this as kind of a way of getting a sense of the level of civilization in different times in history in different places. So I'm not sure how we can translate that to the fish civilization, so to speak. Now, I mean, it's also the case that people wonder, in the past, people have kind of, there's the whole tale of the lost city of Atlantis, which was sort of a very ocean-associated city that is written about in some writings from antiquity. And there's sort of a question, was it real or was it not? The sort of famous example of this was Troy and the whole story of the Iliad and the Trojan War and things like this, which had been written about. And for a while, for many centuries, people thought, oh, Troy was just this mythical thing that had been written about, didn't really exist. Eventually, it became clear in the mid to late 1800s, there was a sort of big excavation effort to find Troy. And indeed, it turns out it did exist as a real city. Somewhat confusingly, like many cities in sort of archaeological finds, it had been built and destroyed many times. So there were like 15 layers or something of different versions of Troy that had been existed, and then things had fallen into disrepair, and then people just built on top of that. And so when it was excavated, unfortunately, some mistakes were made because people didn't know that, like, the Homer's Troy, the one that was in the Iliad, was, layer 5 or something. And it was like, let's go down to the lower layers because maybe they'll be more interesting, and let's use dynamite to kind of blow up the rocks and so on in the higher layers. And of course, that destroyed a bunch of archaeological material, which leads one to these questions about, if you know that there's some amazing archaeological find, do you excavate it today, or do you wait for decades or maybe longer to say, oh, we'll have better technology in the future and we'll be able to better preserve whatever existed in this particular place? But Atlantis is one of these things which is sort of, it's talked about as something that exists, the lost city of Atlantis or whatever, that might have been covered by the ocean or whatever, and nobody knows if it was real or not, or whether it was just a story and a way of describing sort of this alternate, I think it had various kind of political systems that were attributed to it, just a sort of an alternate kind of thing used as a fictional device. I mean, there were plenty of these kinds of things that I'm not quite sure when it originated, but what was it? The city of El Dorado, which was supposed to be the city of gold somewhere up the Orinoco River in South America, that turned out, well, it wasn't real, in fact, even though people spent lots of effort and had lots of expeditions and spent lots of money, and even countries like Scotland famously, I think, almost bankrupted itself through the effort to find this sort of mythical city. Didn't work out. Anyway, just to riff a little bit more on this particular question, one of the things I remember when I was a kid, here's a thing that will happen in the future is, oh, people will be living under the oceans. And there were all kinds of designs and pictures of, what a kind of an apartment building under the ocean would look like. Well, needless to say, that hasn't come to pass. And it's sort of interesting to see what kinds of things like that have happened and what have not. I mean, it turns out people, despite, people have fairly limited kinds of places that they end up wanting to live. I mean, people have, cities, then there were suburbs that were enabled by cars particularly. And I suppose right now, cities have seemed a little bit less attractive after the last year than they had previously. And there's sort of a push to go sort of more out into suburbs. One imagines that one day, if personal aircraft, of some kind come into existence, that the suburbs might spread out further because it will become easier to go, 50 miles out rather than 10 miles out or something. And people have often talked about kind of the exurbs and so on. And the question is, another thing that comes up is, well, if people are going into work in the city, well, then they're going to want to live near the city. But maybe increasingly, just like, well, I've been a remote CEO for 30 years now, the world has kind of sort of caught up with that in a sense, or at least some parts of it have. And it's sort of become clear that more things that you might have thought could be done remotely can actually be done remotely. And some things you thought might be able to be done remotely, it's been kind of not very successful to try and do them remotely, particularly things that involve a lot of kind of human interaction, like education and things like this, turns out doesn't seem to work, although there are plenty of cases where it has been made to work remotely. It's in many situations, it's not as successful as people had hoped, even with technology and so on. But so it's an interesting question. Why did the cities under the ocean never take off, so to speak? I think it's like, what's the point? It's a lot of effort to have something where you are where you're living under the ocean, unless you've run out of space on the land, which we're pretty far from doing. Why would you do that? I mean, sort of the other thing people talk about, and for slightly different reasons, is the whole idea of seasteading, of can you just make your own country and just have this, perhaps it's even an artificial island somewhere out in the ocean, because the way things are set up, there are countries, and within a particular country defined by its geographic borders, that the government of that country is sort of supposedly in control, and there are laws that apply and so on. But then as you get outside some distance away from the borders of that country into the ocean, then outside the territorial waters of that country, wherever they are, 50 miles, whatever the distance is, away from the coastline of the country, kind of the way the world is set up, it's like, okay, it's international waters. There is no country that sort of owns this region of the earth. And there's this kind of elaborately constructed treaty, the Law of the Sea, which was, I think, an example of a place where some of these ideas from things like game theory and so on were successfully used in this very, very multi-party negotiation of how should one make kind of this treaty about how what should be true about ships, for example, that are just out in the sort of open ocean away from cities. But so one thing one might say is, well, gosh, I want to start my own country. Let me have maybe it's a floating platform, maybe it's something that's tethered to the seabed or something, somewhere out in international waters. I've just got this thing that's kind of like my micro country. So people occasionally have tried this. There was a place called SeaWorld, which was an abandoned oil platform in the North Sea, where people just, was it called Sea? No, it wasn't Sea. Oh gosh, I'm forgetting its name. It wasn't SeaWorld. That's the name of the place in San Diego that has lots of aquatic mammals and things. Oh gosh, Sea something or other. Anyway, it was kind of a it was sort of done, I think, somewhat tongue in cheek, with its own flag and its own this, that, and the other. Of course, the problem is, if you just put a thing in the middle of the ocean, it's like nobody is necessarily going to stick up for you if somebody says, well, we don't want that thing to be in the middle of the ocean. Somebody can show up with a bunch of Navy ships and say, we don't like your Sealand. That was the name of the thing, I think. Sealand. Yeah, that was the we don't like your thing, and we're going to blow it up, so to speak. And if you're just this little piece of concrete in the middle of the ocean, it's hard to sort of mount a defense to that. So it's always a bit of a problem. And people talk about this from time to time and say, oh, we're not satisfied with how governments are running things. We just want to make our own, and have something where we can sort of define our own country by making use of land that doesn't yet exist, so to speak. And obviously there's the effort to make artificial islands. That's a whole separate and politically complicated thing in many parts of the world. Well, anyway, that was a long answer to that question. Let me see. Well, there's a question here from SM, can't read the name. What do you think about civilization going to Mars? I think that it sounds really cool. When I was a kid, everybody thought by the 1990s, there would be Mars colonies and everybody would be excitedly living on Mars. One of the questions and the challenges about space in general is, what do you achieve with it? What is the point? What's it going to be good for? And it wasn't obvious when the first artificial satellites in 1957, when Sputnik was first launched and circling around the Earth. One might have thought it was really, other than a kind of a look, this is a cool thing we can do. Its original sort of stated purpose was things like mapping the gravity of the Earth by seeing how the orbit varied as the thing went around the Earth and so on. Clearly, there are more things that satellites turned out to be useful for, like the idea of, well, like, for example, taking satellite photographs of the Earth, being able to look at large weather patterns on the Earth, being able to use communication satellites where you're broadcasting radio signals to the Earth and so on. These are things which were not completely, they were in some respects predicted, but they were not, it wasn't completely obvious that that would be a big win. And it's still not clear whether in the long term, are we going to end up with a lot of satellite-based communications, or is it going to be high altitude drones, or is it going to be fiber optics in the ground? What's it going to be? There's sort of a complicated set of competitions between those different modalities. And so it's not clear what the value of sort of just being in space is going to be. And people wondered, is microgravity, is the fact that one is weightless in space, because one's like in orbit, one's sort of falling just like one would, one's sort of always in free fall, so to speak, when one's in orbit, or at least approximately so. And so everything is weightless. There's no effect of gravity. People have thought at different times, oh, that might be super useful for doing this or that kind of thing. But so far that hasn't really panned out, other than that, people said, oh, that'll be the place where the perfect silicon crystals for the next generation of chips and so on, and all that. So I think the question of, okay, so let's say we put a colony on the moon, what can we do with that? Or a colony on Mars, which is a lot more difficult. Sort of what's the point? Well, one point might be, oh, well, let's extend our civilization to Mars because, gosh, it's at least sort of a backup. I mean, what if the Earth is destroyed by something, Mars will be safe. I mean, I kind of think of that as a little bit of a slightly unconvincing argument, because some of the things that are sort of bad things that could happen, I don't know, the AIs take over the Earth and it's all bad news from there on. If there's any link, it's a kind of a computer security question. How well firewalled is the Mars colony? If there's still data being sent back and forth and, software updates going to the Mars colony and things like this, it's certainly not obvious that the AI that took over the Earth isn't going to wind up in the Mars colony too. And so there's sort of questions like that. I think one of the things is, like, what can one do on Mars that one can't really do on Earth? And one can look at things on the Earth that are examples for that, like how many people live in the Antarctic, how many people populate the South Pole station. And it's turned out there are certain kinds of things one can do at the South Pole that who knew that was a good idea. For example, there's a neutrino detector, a particle physics experiment being done at the South Pole, and it's a good place for that. And that's was not, I think, self-evident when people said, "Oh, we're going to go explore and find the South Pole and so on." And what can we do there? Well, there are obviously things that can be done with in sort of climate studies and meteorology and so on. Although I don't know how essential that has been to be sort of right at the South Pole and so on. And it's obviously very inconvenient to live at the South Pole, and not that many people do it at any given time. Living on Mars is going to be even more inconvenient. And the question is sort of, what's the payoff? And I mentioned earlier, when I was a kid, people saying, oh, people will be living under the oceans all the time. And of course, that hasn't happened at all, because it's just difficult to do. And what's the point, so to speak? Now, I mean, there is a level of point in something like exploring Mars. It's like, it's really good to do these things which are difficult for us, because every difficult thing like that that gets done ends up having a lot of consequences for other kinds of technology. For example, the space program landing people on the moon in the late 1960s was something that drove all kinds of technology, whether it's microprocessors, things to do with materials, and so on. Plus, it was also something that I think encouraged a lot of people, including perhaps me, to get involved with kind of science and things like this, because it was like, look, there are these amazingly cool things that one can do with science and technology, and that has value in itself as kind of a look at these amazing things we can do. It's worth doing for those reasons. But it's an interesting challenge to think about, for example, on the moon, what kinds of things could one do? On the far side of the moon, it's shielded from sort of all the radio emissions from the Earth. We could build some terrific radio telescopes and things. Maybe there are sort of the moon has doesn't have seismic activity. It has no earthquakes because it doesn't have a liquid core. And although I think there are some tiny moonquakes that are of different origin that have to do with the fact that the moon is being distorted by tidal forces, by gravity from the Earth, and that's causing occasional sort of glitches in it. But so one can start imagining, well, it's could one build the giant gravitational wave detector on the moon, which things like that. And then there's the question of, can we mine the moon for something that we don't have on the Earth? One of the interesting things when the first moon rocks were brought back from the moon, it was like, well, actually, these rocks are kind of pretty much the same as the rocks on the Earth. It wasn't known. I mean, it could have been the case that the moon was something which was kind of captured from, wasn't originally formed along with the Earth. It could have been something that was separately captured. And in fact, the current theory for the current sort of leading theory for the origin of the moon, the so-called big splat theory, that's a rather strange theory because it has many steps, says, well, there was this little thing that collided with the Earth, and that caused the Earth to kind of melt and produce all this ejected stuff. And that ejected stuff formed the moon, but also this piece that collided with the Earth is also part of the moon. And if you look at the structure of the moon, although it looks perfectly spherical to us on the outside, the constitution of the rock inside it is not uniform, and it kind of has one big blob on one side, which potentially is something to do with that impact that originally formed the moon. But it could have been the case that all of the moon was very foreign stuff that was very unlike the Earth. I mean, it could have been full of gold or something, which people might have found useful or not. Turns out it's not that way. It's very similar rocks to the Earth. And so the question of, can you mine the moon for something of great value is still an open question. It's certainly the first time there are sort of commercially available moon rocks, people will get them just because they're a cool thing to have. Whether it will turn out that there's some very interesting kinds of rocks that exist on the moon that don't exist on the Earth, I'm not sure. I mean, one thing about the moon, because it doesn't have an atmosphere, on the Earth, lots of kind of rocks tend to get kind of weathered down. So things that would otherwise be sort of sharp breaks, where there's a very, very sharp kind of razor-like piece to a rock, that doesn't tend to exist on the Earth because of wind and rain and all those kinds of things tend to break down those kind of very sharp pieces. But on the moon, there are sharp pieces like that. And so that leads to somewhat different kinds of rock, at least superficially. Maybe internally, the rock is the same kind of thing as the Earth. But at the level of sort of the detailed shapes and so on, it can be different. And that maybe provides some things where, well, I mean, in a sense, it might be like we are used to doing things like cutting gemstones with very specific angles to achieve various effects. Maybe on the moon, there are sort of naturally cut things that are of interest. I'm not sure. Well, okay, there's a question from Derek here. Why do the planets orbit in the same plane? So that's a good question. If in the center of the solar system is the sun, the planets, the Earth orbits the sun, and it's in a particular plane. So the Earth is sort of orbiting around. It's a almost perfectly circular orbit, a little bit elliptical, orbiting the sun, and that plane defines what's called the plane of the ecliptic. It's called that because it's related to the way that eclipses occur. But it's basically the plane defined by the sun in the middle, the orbit of the Earth. Well, it turns out the planets basically all orbit in pretty much the same plane. The Pluto, which used to be considered a planet, is now considered a minor planet, I guess, orbits not quite in the same plane. So it's at an angle to that plane. So why do all the planets orbit in a plane? It's because when they were formed as a kind of a sheet of material around when the sun was formed. So why does that happen? It's sort of the same reason that our galaxy is flat. Our galaxy is a spiral galaxy that's kind of a flat thing. It's something where once things are spinning around, there's a tendency for it to be the case that the sort of this whole disk of accreting material is spinning, and it will tend to be the case that gravity will make it kind of squash into a kind of a pancake. It's spinning around, that's defining which direction will be the direction that it's sort of extended outward in, and that's so all the material, when a star is formed, all the material that's kind of being pulled in, that's making the star, will tend to be sort of squashed down onto this one plane. It's kind of rotating around with the star. And as the planets were formed from that kind of mass of material, that eventually gravity was making that material form into clumps, and those clumps are our planets. And I think that the question of so in a sense, around the sun, the planets are all orbiting. Around planets, there are moons orbiting. And in fact, the moons tend to be in more or less the same plane as the plane of the ecliptic, as the plane in which the planets orbit around the sun. The Earth's moon is actually at an angle of 20-something degrees, 25 degrees maybe. The Earth's moon is at a surprisingly large angle with respect to the plane of the ecliptic. And that's thought to have something to do with this big splat that I mentioned earlier about the way that the moon was formed. But most planetary moons are more or less aligned, like the moons of Jupiter, the first other moons to be discovered by Galileo in 1608. They are in that same plane. And so it's kind of and you can ask about, well, so another thing that is also in the same plane is the rings of Saturn. The rings of Saturn are kind of like an unformed into moons collection of pieces of rock and so on, which for various detailed reasons about the way the moons of Saturn work and so on, those things have not been sort of accreted down into single sort of individual moons. There's still lots of little individual pieces of rock circling around Saturn and making this nice ring pattern. And so one might ask, well, if that happens for Saturn, does it also happen in the solar system? And the answer is yes. The sun has rings around it, and those rings are the asteroid belt, basically, the collection of small lumps of rock, basically, that are mostly between the orbit of Mars and Jupiter. And so it's in a sense, it's like the planets are like the moons of the sun, and the asteroid belt is kind of like the ring of the sun, so to speak. So this question about whether planets tend to be in this plane. Yes, the planets that we have are mostly in this plane. The ones that are more the things like Pluto that were, well, I'm not quite sure why Pluto is not in the same plane. It was, I think, I'm not sure. As you get out to outer bodies in this Oort cloud and things like that, I think that the concentration into the plane is no longer as strong as it is when you're dealing with things that are in the more inner solar system, closer to the sun. And clearly, well, one other question is, if two planets collided with each other, for example, or got very close to colliding, their orbits would be very much changed, and those changed orbits might not stay in the plane of the solar system particularly. In fact, one of the questions is, how many planets did our solar system start with? You know, we think we have 8 right now, but did we start with a lot more planets, or what? And I think the current estimates are that maybe we started with twice as many planets as we have today, and the extra planets were ejected because somehow when they were orbiting around, they got too close to the orbit of another planet, and that led to them to go at a very high speed and at a slightly wrong angle, so that then they would escape the gravity of the sun and become wandering planets, wandering between stars. And so maybe half of all planets that were formed when stars were formed have ended up becoming sort of wandering planets. And I think at this point, we know about, I guess, hundreds of exoplanet systems, places where we can detect the presence of planets around other stars. Most of the time, those are big planets that we detect because those are the easier ones to see. There are no doubt smaller planets as well. And I think that those tend to also form in these planes for the same reasons as our solar system did, that when the planets were formed, it was through this sort of disk that was associated with the formation of the star. Now, an interesting question I realize I don't know the answer to is, our solar system, we have one star at the center. We just have the sun, but there are many binary stars in our galaxy, even ternary stars, where there are 2 stars that are very nearby that are orbiting each other, and they have planets orbiting around the both of them. For example, Alpha Centauri, the nearest star other than the sun, that's a triple star system with 3 stars executing some somewhat complicated orbit with respect to each other. And so they're very interesting possibilities. I don't think there's an example of this yet known, where the planets don't orbit around with all the clump of stars in the center and then just orbiting around those, but instead sort of weave their way between the stars, so to speak, so that you'd end up with strange situations where, what you would imagine in the sky of a planet with a binary star, because the planet is orbiting around the binary star together, what you'd see in the sky is 2 suns that are pretty close together. But if you were in a situation where your planet was threading its way between these stars, you would see a very different and much more peculiar kind of display, so to speak. Anyway, there's a question from King. Are Phobos and Deimos, the asteroids that orbit Mars, are they in the plane of the ecliptic? I believe the answer is yes. And the reason I think I know that is that they are actually closer to the plane than the moon is, because I believe that there is an eclipse sort of every time those moons orbit Mars. So for example, an eclipse is produced, a solar eclipse is produced when the moon is between the sun and the earth. And it so happens that at this point in the history of the earth, the size of the moon as seen in the sky, its size based on how far away it is basically equal to the size of the sun as seen from the earth. So the sun is obviously much, much bigger than the moon, but it's also much further away than the moon. But sort of it so happens that at this time in the history of the earth, the moon and the sun sort of agree in size when you see them in the sky. The moon is gradually getting further away from the earth. And so gradually it will no longer cover the disk of the sun. It will no longer be the same size. It will end up being smaller than the disk of the sun in the sky. But right now it agrees. And so what eclipses happen, solar eclipses happen, a total solar eclipse happens when the moon is just right in front of the sun as seen from the earth. And so you might say, well, if the moon orbited in the same plane as the earth is orbiting the sun, then every time the moon orbits around, every lunar month, every 28 days or so that the moon orbits around the earth, every time it does that, every time it's in the position between the earth and the sun, you would have an eclipse because, gosh, it would be in the way. It isn't that way because there's this angle that the moon, the orbit of the moon is not aligned with the plane of the ecliptic, and that's why it doesn't end up being between the Earth and the sun every lunar month. But my recollection is that for the satellites of Mars, which are much smaller in the sky relative to they are small compared to the disk of the sun, I think, when seen from Mars. But nevertheless, they do cross the disk of the sun. I think that's been seen by some rovers and things on landers on Mars. I think there are pictures of that those kinds of eclipses. Let's see. There's a question here. There's a couple of questions here. What makes a planet a planet? Well, I mean, it isn't a star. What makes a star a star? What makes a star is that it's producing energy through nuclear fusion reactions. It's, well, I say that's what makes a star a star. If I think about a neutron star, which is kind of the end state of a star somewhat more massive than the sun, it's like a giant atomic nucleus 10 kilometers across. That's no longer producing energy through nuclear reactions, but one would still call it a star. So that's sort of an exception to what I'm saying. But generally, your typical star is producing energy through nuclear reactions. A planet does not do that. A planet tends to be something that is, in a sense, there are no situations in which lots of atomic nuclei are being squashed together and fusing and producing energy. If that ever happened, if Jupiter was quite a bit bigger than it actually is, then the force of gravity would cause sort of the internal parts of Jupiter to get squashed together to the point where the nuclei would be pushed together and the nuclei would fuse, they would produce energy, and it would turn into a star. So what you have that is anything that is big enough, what is it, maybe a tenth the size of the sun, maybe a little bit smaller than that. I'm not sure what the lower limit is, and I'm not sure it's completely known. At what point a lump of stuff out there will have enough gravity, enough self-gravity, that it will kind of contract and squash its contents to the point where they will undergo nuclear fusion and it will become a star. The sun is a comparatively large star, and there are stars much larger, like Betelgeuse, for example, is a much, much larger star, which is kind of like the sun, but extended out to the orbit of Jupiter or something. But if you look at the distribution of all stars, the sun is a comparatively large star. Most stars are considerably smaller than the sun. But there's a lower limit to the size of stars, because below that lower limit, the force of gravity no longer is sufficient to make the thing sort of concentrate down to produce nuclear fusion, to produce energy, to make it be a star that's shining and producing light and so on. And so things below that limit, well, they're considered to be planets. Now, if you say, well, if it's a random planet that escaped a solar system, is it still a planet? I don't think we've had to address that question of terminology yet. We've seen so far one interstellar asteroid, this thing, Umanuma, I don't know how to pronounce it well, that came through our solar system a couple of years ago now. And we knew it didn't come from our solar system because it was going way too fast. It wasn't something that would be in orbit around the sun. It was going too fast to be in orbit around the sun. And it was clearly something that had come from another solar system or come from somewhere else in the galaxy. We don't know exactly where. And it's pretty likely that there are such objects coming through our solar system a few times a year at least. But we haven't yet seen anything the size of a planet come through. And obviously that would be an interesting thing to see. And it will be kind of quite interesting to see whether the material and the rock and so on and that, how similar that is to what we find in our solar system and so on. I mean, the thing to understand is that in the evolution of our galaxy, there are different populations of stars. And so in the very first stars, they pretty much get to use the sort of raw material that comes from the very beginnings of the universe, which is mostly hydrogen and about a quarter helium and so on. The elements with very small numbers of protons in them, the elements at the beginning of the periodic table, they are the elements that mostly were produced in the Big Bang at the beginning of the universe. Something like gold wasn't produced in any significant, anything more than infinitesimally in the very early universe. And that got produced by stars being formed. The stars eventually have supernovas where they explode. And in the process of doing that, things of these heavy elements get produced. Now, by the time the Earth came along to be formed 4.6 billion years ago, there had already been generations of stars that had existed, been formed, blown up, produced heavy elements like gold. And that's where all the gold on the Earth and so on comes from, is it's all been processed through these supernovas from earlier generations of stars. So this question so basically any kind of thing that's pulled together by gravity, it's going to form a planet-like thing. Now, it depends on what kinds of elements are in there, whether it's mostly hydrogen and things like that, whether the planet is big enough that it can keep hydrogen gas. So on the Earth, for example, our atmosphere is mostly nitrogen and oxygen. And that is the reason. So if there had been hydrogen gas in the Earth, that hydrogen gas would have escaped into space. And the reason is that there's a certain speed that these molecules are going at. If that speed is more than the escape velocity of the Earth, 25,000 miles an hour, the velocity you need to kind of escape the gravity of the Earth, if the speed of the molecules is more than that, they can escape from the Earth's gravity. If the speed of the molecules is less than that, then they're trapped by the gravity of the Earth and they're kept like in the atmosphere of the Earth. And so it turns out that at the temperatures that exist on the Earth, that nitrogen and oxygen are sort of big enough atoms that the energy that's provided by the temperature is such that the speeds of the molecules aren't large enough for them to escape the gravity of the Earth. But for hydrogen, it is large enough to escape the gravity of the Earth, and that's why there basically isn't any hydrogen in the atmosphere of the Earth. Now, Jupiter, on the other hand, has a much larger escape velocity, and so it is even the hydrogen gas that exists there isn't the molecules aren't going fast enough to escape the gravity of Jupiter, and so a lot of the atmosphere of Jupiter is hydrogen. Now, when you get when you get into the inner layers of Jupiter, it's mostly gas, but when you get further and further into the planet, you end up there are higher and higher pressures. That's the same reason, for the same reason that if you go under the ocean, for example, you go down into the ocean, you'll get very quickly to higher and higher pressures of water because there's just a lot of water on top of you that's kind of weighing down on you to produce that pressure. And so that works on Jupiter too. The center of Jupiter is probably a bunch of hydrogen that's been squashed really, really hard. It's been squashed so hard that it turns into a solid, and actually hydrogen is a metal probably when it's solid. So it's a sort of metallic core made of hydrogen that exists probably in the center of Jupiter as a result of the sort of pressure of all that atmosphere on top, just like under the ocean on the Earth, pushing that core together. So question, let's see, there's a question from memes. Why do most planets, stars, and galaxies seem to spin the same way? I don't believe they do. I mean, what does it mean to spin the same way? I mean, it depends on where, you know, if you have, unless I'm very confused, I think there are attempts to count left and right. How does this work? I'm now confused, because you think about which way is this spinning? You know, you have your thumb sticking out and your hand is going around one way and that's spinning one way. But if you, the point is you don't know which way is up. There's no sort of thumb sticking out of the galaxy. It's just something that's rotating around, and you don't know which way is up. If you knew which way is up, you would know whether it was going clockwise or going counterclockwise, but you don't, I think. I think that there's a, so let's see. There are questions here. Oh gosh, there's a question from Virgil. What did NASA do to avoid astronauts getting huge amounts of cosmic rays? So in the sun, for example, produces light, but it also produces a stream of other kinds of particles like protons and electrons, but particularly protons, and they stream out from the sun. They're produced by processes going on in the sun, and they're like radiation. It's like the kind of thing one wants to avoid, you know, one wants to avoid getting too many X-rays, one wants to avoid the radiation is just particles like protons or electrons or whatever that are going fast, and they're just individual particles. That's kind of so-called ionizing radiation. It's called ionizing radiation because it turns ordinary atoms into ions. An ion is an atom which has had electrons pulled out of it. And so ionizing radiation is you send a high energy proton or a high energy electron through a lump of material, and the electrical effect of the proton, for example, going at that speed will kind of tear electrons out of atoms and will ionize those atoms. And for example, if that happens to the atoms in biological material, you can get all kinds of destruction of pieces of DNA or whatever else associated with just this charged particle kind of barreling through. So it's sort of a bad thing. The typical energy, the energy of cosmic rays from the sun, cosmic rays is kind of the name for this. Well, it's kind of the generic name, although there's also the notion of space weather, where you're looking at just the flux of particles, the flow of particles from the sun. But I guess that one talks about them as cosmic rays, and particularly there are cosmic rays, the peak of the energy is around 1 billion electron volts, which is, oh gosh, how to think about that energy. That's an energy comparable to the rest energy of a proton. So it means that a proton is going at a large fraction of the speed of light. A proton with that energy is going at a very large fraction of the speed of light. Now, most of those particles that come from the sun, the ones that are low energy, particularly the electrons, will be caught by the magnetic field of the Earth and will kind of spiral into the magnetic poles of the Earth. And that's why there's somewhat higher cosmic ray radiation at the poles. It's also what produces things like the aurora, when those high energy electrons kind of interact with things like oxygen in the upper atmosphere. Those high energy electrons make the oxygen kind of, they pull the electrons into a state where when they decay down again, they end up emitting light, and that's what produces the aurora. But in general, there are these cosmic rays are sort of being streamed out from the sun. Now, the magnetic field of the Earth causes, let's see, how does this work? There are these things called the Van Allen belts, which were discovered when early artificial satellites were flown, which are associated with the magnetic field of the Earth. And they are a place where, I guess, the particles from the sun tend to get concentrated and prevented from hitting the Earth. And how does that work exactly? I'm not completely sure how that works. There is I mean, the magnetic field of the Earth is kind of, it's this thing called the magnetosphere. And I am kind of forms this magnetic sheath around the Earth, but I'm now a little bit confused by how that actually works with respect to cosmic rays. But basically, there are in space, so I should say, when a cosmic ray hits the Earth's atmosphere, it mostly just, let's say a proton, most of the so-called primary cosmic radiation is protons. It hits the top of the atmosphere, and pretty soon it hits an atom in the atmosphere, and they both kind of go, they both produce a bunch of other particles, and those particles are quickly absorbed, and nothing reaches the surface of the Earth. Most of what reaches the surface are muons, which come from reactions of protons hit other protons. They produce things called pions. The pions decay into muons. The muons actually decay. If they were at rest, they would decay in about 2 microseconds. But they survive long enough that they get to the surface of the Earth at sea level. And actually, I have on my computer now a cute little device that will actually see the tracks of muons going through my computer. They're about maybe 1 a minute or something, go through a typical something about the size of a person on the surface of the Earth at sea level. If you go up to if you go a mile high or something to Denver, or you go up to some mountain that's twice that height or something like this, you'll get considerably more cosmic radiation. You get considerably more cosmic rays, including some of the primary protons that didn't yet interact when they come through the atmosphere. So in space, you get even more cosmic rays, and so it is the case that there are significant numbers of cosmic rays, and astronauts. One of the interesting phenomena is that if one of those high energy particles goes through your eye, it produces what's called Cherenkov radiation. It's it produces light basically, and even if you have your eyes closed, if one of those particles goes through the interior of your eye, it will produce a bunch of light, which the retina of your eye will say, oh, there's light. It's, one just saw something, even though one's eyes were closed. That's sort of internal, that's an internal source of light. And that's certainly something astronauts report seeing. I think that as you get away from the Earth, even going to the moon or going to Mars, you're exposed to a lot more of these cosmic rays. And when there's a big solar flare or something like that, you can be exposed to even more radiation from the sun of this type. And it's a challenge and an issue how you shield astronauts who are going to Mars, for example. And people talk about putting big tanks of water around the exterior of spacecraft going to Mars to shield for that. It's also not completely clear, I think, what the effect of that kind of radiation. It's like having many X-rays, many CT scans or whatever done. Those are X-rays, which are another kind of ionizing radiation. It's like having many X-rays done on your way to Mars. And does that have an effect? You get tumors, things like that. It's not completely clear what the result of that is. So let's see. There's a question here from King. How exactly do you detect muons? Okay, so there are a variety of ways to do it. Essentially, what you're detecting is that process of ionization. When there's a charged particle, a muon is a charged particle, like an electron. It has the same charge as the electron. A muon is kind of like an electron, except it's about 206 times heavier than the electron. But a muon is coming through and it is ionizing, it is producing this, it is turning neutral atoms that have an equal number of protons and electrons into atoms where some of the electrons have been torn out. And so you can detect that because there are electrical effects of that ionization process. And typically what you have to do, there are several different methods. The very early method was things through Geiger counters or Geiger tubes. And the way those work is, okay, here's basically the idea. You imagine that you're going to make a piece of electric discharge. So for example, when a lightning strike happens, that's happening because the electric potential of the clouds is much higher than the electric potential of the ground. And what's happening is it's essentially the voltage is the difference of, it's like you have a very high voltage thing and you have your, a million volts between this thing here and the thing on the ground. And the question is, when you have a high enough voltage, it will be the case that materials break down. With a high enough voltage, voltage is kind of how hard you're pushing electrons to go through a material. When you have a high enough voltage, eventually you'll be able to push electrons through basically any material. And so you get this phenomenon of discharge. So you see that if you have, when you have a spark, for example, through air, it's usually pretty hard to push electricity through air, to push the electrons through air to make an electric current. But if you push hard enough, the air will break down and you'll get this trail where you have a sort of a spark where the electrons will be moving through the air. So every material has a certain breakdown voltage at which it's actually voltage, it's voltage per distance. A certain maximum, actually it's the electric field, which is voltage per distance, a maximum value of that before it will just break down and say, forget it, I'm going to let the electrons just go through. Well, so in a Geiger counter, what's done is to make it so that you have something where you have a high voltage where you get a gas. So it's right at the point where it would have this electric discharge, but it isn't yet having that electric discharge. And when the gas gets ionized, gets this ionizing particle go through, then the electric discharge will happen in that place. And so you'll often, they're usually seen in kind of old movies at this point, this kind of click, 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 click sound from a Geiger counter. And when it detects radiation, the clicks get faster, faster, much faster. Each of those clicks is a little, in a sense, lightning strike inside the Geiger tube, because it's a place where there is electrical breakdown of the gas, where the gas was held at this very high voltage, and just in places where the particle went through, you detect that particle, and it makes this kind of clicking sound. Okay, so that's sort of one form of particle detection. There are several forms of particle detection. There are much fancier versions of that, where you have a whole array of wires, and they're all maintained at high voltage. And so you can then detect where the track of the particle goes, because you can see which wires which when the electric discharge occurs, where did the electricity go with respect to these wires? And that's one kind of method. And sometimes you can do just timing information where you say, oh, I've got this long wire, and I can tell that this kind of lightning strike, little miniature lightning strike, happened at this particular moment relative to the voltage that I put down this wire and so on. And I can measure the time delay, and that tells me where on the wire the particle was detected. There are a variety of other methods of particle detection. Two major other ones are things called scintillation counters and semiconductor detectors. So scintillation counters are basically a kind of plastic where when the particles go through, they produce the interaction of the particles with the material in the plastic excites the atoms to the point where they emit light. It's very similar to what happens in the aurora, where the charged particles that are spiraling in from cosmic rays interact with things like oxygen and nitrogen in the upper atmosphere. They make those atoms go into this kind of excited state, and as the atoms decay, they emit light. And it's the same kind of thing in a scintillator. In a scintillation counter, you have these big kind of usually plastic paddle-like things. At least they used to be that shape. I'm not sure there was that shape anymore, but there would be a sort of flat blade, and you would, and then there would be a kind of, what would happen is there'd be a flash of light somewhere in this plastic where the particle went through, and you would kind of use it like a piece of fiber optics. You would concentrate. You would kind of everywhere in this lump of plastic, you could detect light that was generated anywhere in the lump of plastic in sort of the base of the paddle, and you could then measure that amount of light with essentially a camera. It used to be a so-called photomultiplier tube, which is a very sensitive kind of camera-like thing. Okay, so that's the second method. The one that's become popular in more recent times, and the one that the little USB device that I have on my computer is based on, is semiconductor particle detection. I mean, I have to say, many years ago, well, okay, so when you have something like a memory chip is a piece of semiconductor, and it has all these little wires on it and all these little transistors on it. And when an ionizing particle goes through, it basically dumps electricity into the memory chip. So it's that ionization is sort of a let's add some more electrons in this place. Well, the memory of a computer is based on having electrons present or not present at particular places defined by these transistors and these wires that cross over and so on. So when an ionizing particle goes through, it's like dumping a whole bunch of extra electrons there, and it is what you thought was a 0, for example, in your memory. It's like, well, no, it just got changed to be a 1. And so the way semiconductor particle detectors work is they're kind of like memory chips, except that what one's doing is one's looking for the errors that occur in the memory chip. One's looking at the places where a cosmic ray went through that caused the memory chip, the bit that was stored in memory, to change. And because the memory is kind of laid out in an array, and you can kind of tell, well, it was the bit at this particular memory location that changed, it tells you where on the memory chip the particle went through. And I have to say, I remember back in the late 1970s, I was talking to my friends in particle physics, experimental particle physics, and saying, you know, it has to be the case that these semiconductor devices, that we know that there are problems that happen from cosmic rays in semiconductor devices. Surely you could use that as a particle detector. And they were saying, no, couldn't possibly work. But anyway, a few decades go by, and that's a very common way of detecting particles. Now, it has to be said that one of the issues is with cosmic rays and memory chips and CPUs in general, microprocessors in general, is yes, when ionizing particles go through, they dump electricity into these things, and they mess up the operation of they mess up the data in the memory chips, they mess up the operation of CPUs and so on. And so that means when you put electronics into satellites, for example, which are exposed to cosmic rays, or you send them to Mars or whatever else, you have to be very careful about arranging for about those microprocessor chips to make sure that their operation is not just scrambled by cosmic rays. And so one way to do that is to have is to have shielding around. So it turns out that, at least for charged particles, actually it's true in general, the heavier the element, heavier in the sense that it has higher atomic number, more protons and neutrons in its nucleus, but for charged particles, most important with protons. The heavier the element it is, the better it will shield ionizing radiation. And so lead is usually the best shielding, and that's what you'll see, if you get a dental X-ray or something, and somebody gives you this lead apron, it's lead because the X-rays are stopped much more efficiently by lead than they are by lighter elements. Lead being the sort of heaviest, easy to acquire element, and in fact, at a mathy level, the amount of stopping goes up like the square of the atomic number of the element, so in any case, so when you put electronics on satellites, you can shield it. You can also use electronics that's been hardened. It always used to be the case, I don't know if it's still true, that you could buy the mil spec, the military specification version of pretty much any kind of microprocessor, and that would be hardened against certain kinds of electromagnetic pulses and things, and it will be the better thing to use if you're putting it in space. But in any case, so the way that you detect these particles is also the thing that causes trouble for electronics. And you can, by looking, for example, in a semiconductor detector, exactly where did the particle go, which particular memory locations got scrambled, you can see what the track of the particle is. I was going to mention that it always used to be the case that when computers were installed in high altitude places, famously like the Los Alamos National Lab in Los Alamos, New Mexico, which is about 7,000 feet, it would be the case that there would be more cosmic rays there. And so there would be more errors in computer memories and so on that would exist there. This became sort of a non-issue because most serious server computers have error correction, which means they have extra bits of memory that are included, which are used to check the rest of the memory so that you can check, because most cosmic rays would just lead to a single bit error. So you can usually correct that with the error correcting memory. Other kinds of electronics, like mobile phones, for example, typically don't have error correcting memory, or haven't in the past had error correcting memory. And it's sort of an interesting question why one doesn't see more effects from sort of, a cosmic ray went through my phone. And actually there have been various possibilities of using phones as a big detector of cosmic rays. Actually, there's a different way to do that, which is if you black out your phone camera, then the device, the charge-coupled device that is the thing that detects light in your camera, if a charged particle goes through it, it will generate what appears to be a little flash of light. And so there have been various projects that say, let's take a whole bunch of cell phones, let's cover their cameras, and let's measure the light that comes even from the covered camera, so to speak, and use that to detect cosmic rays. The typical cosmic ray from the sun has an energy I was mentioning of 1 GeV, and the units of these things, 1 billion electron volts. That unit means if you have a 1 volt of potential difference, then 1 electron volt is the energy that would be given to an electron that has sort of fallen through that voltage, so to speak. It's the push given to a single electron by 1 volt is 1 electron volt. So anyway, that's a way of measuring energy. The highest energy cosmic rays that have been observed are around 10 to the 21 or 10 to the 22 electron volts. So they are so energetic, they are like 1 joule of energy. They're enough that they're from like throwing an object, a big object, and just throwing it at a reasonable speed. That's the same amount of energy as is packed into a single proton for the very highest energy cosmic rays. There are very few very high energy cosmic rays. One of the things that happens is, just as there are particles that are trapped in the magnetic field of the Earth, there are also particles that are trapped in the magnetic field of the galaxy. And there is I think it's 10 to the 15 electron volts is the maximum energy of cosmic rays that are trapped, of particles trapped in the magnetic field of the galaxy. And then there's a very bizarre thing that happens around 10 to the 19 electron volts, I think, a very strange phenomenon. So if you have a proton and it has that high in energy, it turns out you might think, the proton is just going through interstellar space, intergalactic space. There's nothing for it to hit. But actually there is, because there's the relic radiation from the Big Bang, the cosmic microwave background. And that consists of a large number of low energy photons, low energy particles of light that are just spread out throughout the universe. We detect them on Earth as radio radiation, as a tiny radio signal, so to speak. But they're just photons that are sort of scattered throughout the universe. And when you have a sufficiently high energy proton, it can actually hit one of those photons that is in the cosmic microwave background, and it'll scatter from that thing and it will typically lose energy as a result of that scattering process. So you have this incredibly low energy photon from the cosmic microwave background, this incredibly high energy proton, and if the relativity tells one things about how that scattering process works. What matters is the energy of the proton multiplied by the energy of the photon, the square root of that, and that can be big enough that there's a substantial chance of that process happening, and that it scatters the proton out of the way and causes it to lose energy. And so that was a reason why people thought there might never be cosmic rays above about 10 to the 19 electron volts. In fact, cosmic rays maybe 20 or 30 years ago, cosmic rays above that limit were observed. And that kind of tells you something about how far the cosmic rays have been coming. Because if they've been tooling along halfway across the universe, the chances are they will have hit a piece of cosmic microwave background before they get to us. So it kind of tells one that even these high energy cosmic rays are coming from inside our galaxy. And so then the challenge is on, where do these very high energy cosmic rays come from? Do they come from some of these quasar, blazar type things where there's these astrophysical jets that are very high energy jets of particles, and light that are probably associated with matter being pulled into black holes and all kinds of exotic things like this. I think there's a question here from RJ. Why is water a good radiation shield if it has low atomic numbers? It's not okay. So this is a little bit complicated. With ionizing radiation, like a proton, the main thing that's causing a proton to get stopped by a material is scattering from the nucleus through electromagnetic processes, a so-called Rutherford scattering. It was discovered by Ernest Rutherford, who was the person who discovered the atomic nucleus, in fact, by noticing the scattering process, that you shoot a proton at a nucleus. The proton is positively charged, and the nucleus is positively charged. That means, at least if it gets that there will be a repulsive electrical force between the proton, because like charges repel, the proton and the nucleus will repel each other. But that force of repulsion isn't particularly strong unless the proton gets really, really close to the nucleus. And then there's this inverse square law, and that inverse square law, when the distance is very small, the force will be very large, and that causes the proton to scatter. And that's sort of one of the effects. Okay, so that's for a proton. What about a high energy photon, like a gamma ray or an X-ray? How does that get stopped by matter? Well, what happens is, oh boy, there's all kinds of physics here. What happens is the photon is coming through the material, and the photon will turn into an electron-positron pair. If the photon has an energy that is larger than the rest energy of a proton, of an electron plus a positron, then when that photon is kind of kicked by the electric field of an atomic nucleus, it will do what's called pair production. It will produce an electron-positron pair. And that electron-positron pair are then charged particles, and then they scatter from atomic nuclei in the same kind of way that protons would scatter from atomic nuclei. So that's the way that. So when a high energy photon comes into a material, there's this sort of conversion process that happens where it is converted into electron-positron pairs. The electrons and positrons, they actually produce additional photons, which again, that could get converted. And you have this whole cascade, this whole shower of material that gets a whole shower of particles that are produced. And so and what ends up happening to these electrons in the end, they get captured by an atom, and they kind of spiral into the atom and eventually get captured there. So so for photons, you need conversion of the photons into charged particles, and then there's this cascade process. And I'm thinking that cascade process, let's see, is that directly dependent on atomic number? I think it is. I think it also is, just like for protons. Okay, the next case is neutrons. Neutrons are neutral particles. They do not, there's no electrical process that will deflect a neutron. To deflect a neutron, you have to, it actually has to hit an atomic nucleus, and the strong nuclear force, which is the force between protons and neutrons and so on, has to take effect. And that's how you kind of stop a neutron. And the issue is that actually there's another effect. Is that an important effect? The neutron has a magnetic dipole moment. It's like a little bar magnet. And it does have, it is not a charged particle, but it is a particle that has a magnetic effect. And is that important? Oh gosh, I've forgotten. But in any case, the fact is that, no, it isn't important. That's not important. That's not the main effect. So neutrons, the main place where lots of neutrons get produced is in nuclear reactors. And so there's sort of a big issue of how do you stop the neutrons in a nuclear reactor, because the neutrons are what go from one nuclear process to another. That's what leads to chain reactions in nuclear reactors, is mostly neutrons that are being that are produced from one atomic one nuclear fission, for example, and they go and hit other nuclei, and they cause those nuclei to fall apart, and that produces more neutrons, and those cause more nuclei to fall apart. Pretty soon you have this chain reaction. So in a nuclear reactor, to control that chain reaction, you want to absorb those neutrons. And there's a lot of detailed information on different kinds of materials that are so-called moderators that absorb neutrons. And that was this big thing. People have spent a lot of effort measuring neutron cross-sections, neutron probabilities of interaction for different materials. And so, for example, heavy water, deuterium oxide, which has where the hydrogens in the water don't have just a single proton, but a proton and a neutron, that has very different characteristics in terms of absorbing neutrons from ordinary water. And so that's they're so-called water moderated reactors, and I think they're heavy water moderated reactors. And these are things to do with neutron absorption, which works differently from charged particles, which have this dependence on the atomic number. Well, we should wrap up soon here, but let's just see if there are any other related questions here. Why does an iron core result in a supernova? Actually, in a supernova, so you have a big star, a bit bigger than the sun. The star is usually, what's happening is protons are crashing together at a very high speed and are fusing to produce two protons are crashing together. They're like hydrogen nuclei, and they're fusing together to produce helium nuclei, which have two protons in them. And that process of the protons, it takes a lot of energy to make them crash together, because you have to overcome the fact that they're electrically repelling each other. And so at sufficiently high temperatures, you can push those protons together. When they get close enough, they'll fuse and they'll release energy. And that's the primary energy that's produced by the sun, is from proton burning, so to speak, or hydrogen burning, from hydrogens fusing and producing helium. But then some helium also fuses together and it produces heavier elements and so on. Okay, so what happens is eventually a star will have pretty much used up all its hydrogen. All its hydrogen will have been converted to helium. Maybe the helium will have been converted to lithium, and it'll keep going, so to speak. And as the star kind of uses up its nuclear fuel, it is less able to keep itself. It's less able to produce energy to kind of keep the pressure of the star, keep the star kind of pushed out and not crushed by gravity. And what happens is, when it uses up a bunch of its kind of nuclear fuel, when it uses up a bunch of the lighter elements, because they've all fused into heavier elements, then it can no longer has enough pressure to withstand collapse from gravity. And this happens rather suddenly. And it happens, I think, around the time of oxygen burning, silicon burning. I think those reactions start happening rather rapidly. And when those start to happen, the pressure produced in the star rapidly decreases, and the star will just collapse. The outer regions of the star will just be pulled by gravity very rapidly in, and the whole thing will crush down into something much smaller. When that happens, there's a huge amount of energy associated with that crushing down process, and that then causes more nuclear reactions to start up that weren't able to start up before because the star didn't have enough temperature to have enough energy for the individual nuclei to produce some actually I'm saying something slightly wrong here. So the star starts collapsing, and what happens is things like silicon burning and oxygen burning. It's not burning in the usual sense, it's nuclear fusion. Those things start to happen. It takes more energy, if you have two silicon nuclei, they're pretty big, they have pretty big electric charge. You need to push them together much harder. You need to push hydrogen nuclei together to overcome the force of repulsion from the electric charges. And so it takes a higher energy, a higher temperature to make that happen. But that temperature is achieved when the star is collapsing. In that moment of collapse, it suddenly will achieve those higher energies, higher temperatures, and that will cause new nuclear reactions to start up. And that happens very suddenly in matters of seconds or less. Those new nuclear reactions will start up, and then kaboom, the whole star explodes, because there's been this huge amount of energy released, that newly released, that will just throw everything all over the place. And there's usually that's the point at which heavy elements get produced, because the way that nuclear reactions work, anything beyond iron, it's not possible. When you're getting energy by pushing nuclei together, you don't gain energy by pushing nuclei together when you go anywhere beyond iron. Beyond iron, it starts to go the other way. And when you get to things like uranium and plutonium, when you split those nuclei apart, you get energy. But the minimum energy point is iron 56. And that's the place where kind of everything, you get energy by pushing things together to get to iron, but that's as far as you can get with that. But at the point where a supernova is happening, you're pushing things together so hard that it doesn't matter, that you're just pushing these nuclei together incredibly hard, and that's how you form. That's one of the processes by which you form heavy elements. It's so-called rapid process, R process, nucleosynthesis. And that happens in the moments of a supernova, and that's where some fraction of the sort of the gold in the world comes from, and other heavy elements. The other process is a slower process, which is the result, I think, of high energy of nuclei that are produced by the supernova and that are sort of streaming outwards at a high energy, and they're gradually interacting with other nuclei that were in the exterior of the supernova. And that's a more gradual process that, again, is a process that creates heavier elements. Well, okay, maybe one last question here, which is from Cap. How do nuclear blasts affect computers? We already talked about a little bit of this in effect earlier. The main thing, when you have a nuclear blast, you get lots of radiation produced, lots of charged particles produced by the nuclear reactions. You also get a lot of energy released that produces a shock front that's just like just literally physically moving the air and so on fast. But there's another thing that's produced. It's called the electromagnetic pulse. And that is produced by rapid ionization, I think, of the air near the nuclear explosion. I think that's the source of it. So in other words, it's the nuclear explosion happens, it's releasing a lot of energy, it's producing lots of ionization, it produces it makes the atmosphere, for example, but actually this happens in space as well. So it's the main point is that there's a lot of charged particles that are generated in the nuclear explosion, and those charged particles are made to go fast, and they're accelerated a lot. And whenever a charged particle is accelerated, it emits electromagnetic radiation. That's just a feature of the way that electromagnetism works, is that when you accelerate a charged particle, it produces electromagnetic radiation. That's how radio antennas work. And in this case, you have all these particles that are very high energy, and they produce a whole bunch of electromagnetic radiation. In particular, they produce this pulse of electromagnetic radiation that is across a whole range of frequencies, into radio, down into microwaves, et cetera, et cetera, et cetera, even to visible light and so on. But that pulse, that electromagnetic pulse, is something which has a really bad effect on computers, because it's like putting this, it's like having kind of a, it's kind of almost like having a lightning strike go through the computer. Not quite, but it's sort of the same idea of this very intense pulse of electricity going through the computer. And so what tends to happen is low voltage electronics like microprocessors and so on can get completely destroyed by electromagnetic pulses. And so that was during the Cold War, that was sort of a big deal that particularly American electronics was being made with sort of low voltage microprocessors, semiconductors, all that kind of thing. Soviet electronics, people were saying it's really very primitive. It's using vacuum tubes, and much higher voltage electronics. But one feature of that kind of lower technology electronics was that it was much less subject to being destroyed by electromagnetic pulses. I think there are better ways to harden microprocessors that are now known, but basically it's sort of bad news for microprocessors when they're subjected to an electromagnetic pulse from a nuclear explosion. And that's one of the reasons why, if, for example, there was a nuclear explosion in space, it would destroy the electronics of lots of satellites. The satellites that weren't in the shadow of the Earth would tend to get destroyed by that pulse. And that's one of the many reasons why let's hope nobody ever detonates a nuclear explosion in space. But in any case, with that perhaps not so positive thought, I think we have to wrap up for today. Lots of interesting questions here. I look forward to being able to address more of these next time. Well, thanks for joining us, and